All right, quantum mechanics in a nutshell. What exactly is quantum mechanics? So it's a study of the electron, everything about it, its location, how it behaves, its different properties. So we're going to go into that. The first thing we need to understand in order to understand an electron is that it has two different ways of looking at it. You can look at it as a particle or you can look at it as a wave. We're going to focus primarily on waves. That's the most common way you need to be aware of it. So in order to understand how it behaves as a wave, you need to understand what a wave is to begin with. So what exactly is a wave? Wave is basically anything that is able to travel, cause energy to travel, which in this situation, there's a couple different features you need to be aware of. First, you need to be aware of what's called the wavelength. The wavelength is the distance between two crests. So crests are basically the top of the wave, or two troughs, which is the bottom of the wave. So you can call it the top and bottoms, it doesn't really matter. But the key is it has to be the distance between the two tops or the two bottoms. You'll get the same wavelength each way. The number you come up with is called the wavelength. So when we say it has a wavelength of 300 nanometers, what we're implying is the distance between this wave and this wave, or these two crests, are exactly 300 nanometers. That's what we're trying to represent. So make sure you understand that. So frequency, on the other hand, is the number of waves passing a given point per unit of time. So what is that in English? How many times a wave, like let's say this is your point, how many times the wave traveled through this location? So obviously the more it travels through it, the higher the frequency. And what dictates that? The length of the wave. Long waves, as you can kind of imagine, it's going to take a little longer for it to get through this point each time. Whereas smaller waves, because of close distance between two different crests or different troughs, are going to get through it pretty quickly. So which one needs this higher frequency? This does. And the reason for it, shorter wavelength. So right there you have one of the more important relationships about waves and frequency. They're inversely related. So as frequency goes up, which is represented by the letter V, so as it goes up, your wavelength, which is represented by the symbol lambda, decreases. They're opposite of each other, and vice versa. If the frequency goes down, then your wavelength goes up. So they're opposites. Big wavelength means small frequency, and vice versa. All right, the first type of waves we're going to focus our attention on is electromagnetic radiation, which is basically the whole spectrum, all the different waves that we know in existence. It goes from gamma rays, which are most energetic, and you could tell it's the most energetic because look at the value, 10 to the 20. That's a very large number. And if you do a comparison between that and this side, which is radio frequency, you get 10 to the 4th. So this obviously has a lower frequency than this. Why? Because it's a smaller number. Then we represent frequencies either with S to -1 or with the unit hertz. They're synonymous. They're one and the same thing. So whichever one you see, it both represents frequency. And if you notice, this has the smallest frequency, but guess what? It has the largest wavelength. And you could tell because you're going from 10 to -11 to 10 to the 3rd. This is a much bigger number, some much bigger wavelength. So radio frequencies are very large waves. What's the significance? Well, because they have low frequency, they're not going to hurt you. They don't cause any damage. That's why we have radio frequencies all around us, radio waves all around us. On the other end of the spectrum, you get hit with gamma rays. That's a lot of pain and damage. Why? Very high frequency, very low wavelength. So the most energetic or dangerous ones, if you will, are on this side. So you can see gamma rays the most dangerous, highest frequency, followed by X-rays. That's why you don't get a lot of X-rays. You increase the probability of cancer and other issues. UV, you've all got burned outside. It's mainly because of UV, right? Ultraviolet light. The reason it's called ultraviolet is because it's beyond violet. So if you want to look at it, visible light is basically G BIV. So red, orange, yellow, green, blue, violet. And that's what this is showing you here. So which one of these is the lowest frequency? Red. Why? Highest wavelength. It's the least dangerous. This is why red lasers are very common. It could damage your eyes, but not as much damage as a 400 nanometer blue light can. That could create a lot of damage. And that's why you don't see them very often, if at all. So ultraviolet means beyond violet. So violet's the last color in the spectrum. This is your color spectrum. So ultraviolet means beyond that. So that's more energetic than visible light. But here's the funny thing. Microwaves are actually less energetic than visible light is. Go figure. Because you know microwaves used to cook your food. So how the heck is it the light, regular visible light's more dangerous in terms of energy? That's the way it is. That's the energy production. Infrared is what you let out on an everyday basis, and this is what infrared goggles allows people to detect is your infrared energy, because you let out that wavelength whenever you are alive, and in the dark you could even see that. So important things to note here is the relation between wavelength and frequency and the different ones you have, the different colors and their energies. Colors, by the way, are between 400 and 750 nanometers. It's important to note. That's your color spectrum. And the relationship between lambda and V is such that if you multiply the wavelength times the frequency, you get the speed of light. Speed of light is this. This is how fast light is traveling. I do want to make clear, all these different waves are traveling at the exact same speed, all at the speed of light. They don't fluctuate because this is energetic or this is more energetic. None of that matters. The only thing that matters is you understand that the waves of any sort all travel at the speed of light. The value for this, meters per second, 3.8, is a constant. So what this allows you to do is actually figure out the frequency if you have the wavelength, and the wavelength if you have the frequency. It allows you to figure out either one if you have the other. So that's the importance of this particular relationship, is that if you want to figure out the wavelength, for example, you could say wavelength is equal to C over V. If you want to figure out the frequency, you could say it's C over lambda. That's important. All right, calculation involving waves. So you C equals lambda V to calculate frequency or wavelength. Really doesn't matter which one. Use E to calculate the energy. And the way you calculate the energy, you need the frequency. So if you multiply Planck's constant, which is 6.626 times 10 to negative 34, we're going to ignore the units for now, and you multiply times the frequency, you can actually get the energy. So here's the cool thing. You can go from the wavelength of a substance or a wave and then actually get how much energy that particular wavelength has. So you can figure out the energy for a 400 nanometer color, like red. Pretty cool. Sorry, 400 would be blue, not yellow, not red. All right, H is 6.63 times 10 to negative 34 joules per second. Joules times second, not per second, my apologies. All right, so the other thing we need to understand about energy is how energy can be explained using the shells in an atom. So these are the different shell possibilities: the first shell, second, third, fourth, fifth, sixth, and then so on. Theoretically, we can go on to infinity for shells, but we know the periodic table only has 7 periods. There's only 7 shells. So things you need to know, atomic theory-wise: explain that electrons exist in specific quantas or shells. So an electron exists in a second shell. Doesn't mean it could jump to the third by itself really easily or anything like that. It has a very specific energy. So every electron has a very specific location. Now this is a departure from the solar system model you're probably accustomed to for the atom, where the electrons are rotating around the nucleus like planets around the sun. That's not really what happens. But the electron does exist in a specific shell. So if they're in the third shell, they are in the third shell. And they have a certain amount of energy because they're in that location. So electrons are located in specific energy levels. Electrons have specific energies. So each electron, based on its location, has a specific energy. And I do want to emphasize, the further you are, the more energy your electron has. So an electron in the 6th shell actually has more energy than one in the 1st shell. That's important, because it explains why if I'm going from the 1st to the 6th shell, I need to put energy in to make it happen, because this is lower energy than this. We'll come back to that principle a little later. Energy is absorbed or emitted to move electrons between energy levels. So you could either absorb energy to go from the 1st shell to the 3rd, 4th, 5th, 6th, 7th, or you could lose energy to go the other way, to go from the 6th shell to the 3rd, to the 2nd, to the 1st, whatever. The calculation allows you to figure out that energy is this thing. This is the Rydberg formula. So it tells you the change in energy, you need to go up or down, is equal to the negative RH. That's the negative part of the formula. RH is 2.18 times 10 to the negative 18 joules. 1 over NF squared. NF is your final shell. So let's say, for example, I'm going from the 1st shell to the 2nd shell. Your NF would be 2, and you would squared. So it'd be 1 over 4, basically. Your NI is your initial shell. So we went from the 1st shell, so it'd be 1 over 1 squared, which is basically just 1, right? So 1/4 minus 1 will give us, times RH will give us the energy. Now, you'll note that 1/4 minus 1 gives you a negative number, right? Because 1/4 minus 1, you do this thing, you basically get negative 3/4. Why is that important? Well, when you multiply the negative here times the negative here, what do you end up with? Positive number. Why is that important? We said we went from the first shell to the second shell. That's an endothermic reaction, right? You're absorbing energy. Thus, you get a positive number from this because of that. So it has to make sense. So if you know you go from the first and the fifth shell and you end up getting a negative number, something went wrong. You need to put energy in to make it go up, because it has to absorb energy to go up and release it when it comes back down. All right, so here's an example of these different formulas being used. So the first example, the yellow light given off by sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. Pretty small wavelength. What is the frequency of this radiation? All right, so frequency is really straightforward, right? You just equal C equals lambda V. We arrange it to solve for V, and it's very important. Once again, you isolate your variable before you start plugging numbers in. It's very easy to just say C equals lambda V, plug in your numbers, and do the math. Don't do that. Isolate your variable before you even start putting numbers in. It makes it a lot simpler. So then we set it up. Now, in order to use this calculation, our units for wavelength has to be in meters. Why? Because C is in meters per second. You want meters to go away, so you're left with S to the negative 1, which is the units for frequency. So if you don't have this in meters, this whole thing goes to poop. So how do you do that? Really easy. Just multiply, and you don't have to do this whole T-chart if you don't want to. Just remember, whatever number they give you in nanometers, multiply by 10 to negative 9, which just means stick it at the end. There's your value in meters. Pretty simple. You could do it a more interesting way, but why? So your V is equal to, notice the meters to meters, so this goes away. That's how we know to do it correctly. We do the math, 3 times 10 to the 8 divided by 589 times 10 to the negative 9. I didn't even put the scientific notation. Why didn't I? Because I don't care. I want to make the math as easy for myself as possible, and the only time they really care about the units is at the end. And if you notice, you have 3 sig figs here, so you need to have 3 in your answer. Your sig figs are based on the values they give you, not on the constant. The 3 times 3.1 to the 8, that's a constant value. We don't base our sig figs on that typically. We base it on numbers we're actually using, so be aware of that. So in this situation, when you do the math, when you divide this by this, you get 10 to the 14 S to the negative 1. Remember, this is the same thing as saying hertz. So 5.09 instead of 14 hertz, or S to the negative 1. Really doesn't matter which one you use. That's the frequency. That's a pretty large number. Now we could go on to figure out the energy to get a better idea of how big that is. So let's do that. So now we're going to calculate the energy of one photon of yellow light whose wavelength is 589 nanometers. Remember, these are only for single photons. When you're doing these calculations, it's basically one packet of light. What's the difference? We're not talking about a mole of them, which is 6.02 to the 1023rd of them, which is more logical because you don't just get hit by one photon, right? You get hit by a whole bunch of photons. But for our purposes in these calculations, we're going to base it on a single photon. That's important. Because if I want to do it for mole photons, I would do this calculation and then I would multiply by 6 times 10 to the 23rd, because that's the number you need to go from moles to any number of particles, right? So for this one, we're not going to do all that. There's our frequency again. I use the same values from the previous question. I'm just showing it to you again. So there's your numbers, right? So we need to calculate energy. So remember, energy is equal to H times V. So H in this situation is 6.626 times 10 to the negative 34. It's a constant given on the cheat sheet for the AP exam, so like you have to memorize it. Multiply times your frequency, and then there's your energy. So a single photon, one of them, produces this much energy. This is per photon. So what if you have, hypothetically, this is per one photon. So remember what I said, a mole? What if I'm interested in a mole of them? So what about 6 times 10 to the 23rd photons, which is 1 mole. So if you want to know how much energy is produced per 1 mole of it, you can multiply this together, which, you could kind of guesstimate here. That's like 18, 19 times 10 to the negative 19 and 23rd is about 10 to the 4th. So about 1.9 times 10 to the 5th. All I did is move the decimal point once to the left to get from the 4 to the 5. So that's joules per mole. So just in the event they ask you for a whole mole of them, understand that these calculations are based on a single photon. So if they don't use the word mole in the sentence, don't worry about this. You don't need to do it. But if they do, you got to do this. All right, calculate the wavelength when an electron goes from 2 to 5. So the difference between this and the last one we had a wavelength. This one we have energy level. So you're going from the second shell to the fifth shell. Before I even crunch any numbers, I know it's absorbing energy, so it's endothermic. I know you need a positive number. You got to think like that. But let's verify. So here's our formula. We plug and chug. Notice F and F was 5. That's why it's 1 over 5 squared. The 2 was your initial shell, your Ni. So plug and chug. You get this. Notice 0.04 minus 0.25. You could tell it's going to give you a negative number from there, right? Negative times negative gives you a positive. So you're good to go. There's your energy for this particular photon, a single one. Remember, you're not doing a whole bunch of them. You're doing one of them. Jumping from the second shell to the fifth shell, this is how much energy you have to put in. That's all this represents. The energy you need to go from the second to the fifth shell. And if you want to calculate, in this situation, you're asking for the wavelength. So this is the energy, but we want the wavelength. So what do? Well, we know that we can get the frequency from the energy. So we figure out the energy first, right? Now we're going to figure out the frequency. So we're going to rearrange that formula, solve for V, which basically means E divided by H, which gives you that. It gives you 6.9 times 10 to the 14 s to negative 1. Okay, that's our frequency. So I'm working backwards here. It's a lot of work. All right, you got to get your energy based on just that specific photon, go from the second to the fifth shell, and now you need to go a step further. So for this part, there's your wavelength, which becomes 434 times 10 to the negative 9 meters. And if you want to convert this to nanometers, it's that. And for those wondering, how the heck did I do that? Well, remember we multiplied by it to go from meters to nanometers? Well, we're going the other way, right? So technically here, you would go 10 to negative 9 meters again, and 1 nanometer. So what you're basically doing, you're dividing. That's where this is coming from. And if you notice, these 10 to the negative 9s cancel out. Just coincidence, they're the same value. Meters cancel out like they're supposed to. I'm left with this as my answer. So you're looking at what energy-wise, this is going to be a blue-violet area because it's on the low end of the frequency, wavelength spectrum, and smaller the wavelength means more energy. So that's what we're looking at. This is the color light you would see, which is fascinating because now you can actually use the energy calculations and the way, going from the energy, you can go all the way to the wavelength and get the color. You could tell what color you're supposed to see. How cool is that, right? All right, so now let's go on to quantum mechanics. So we have the basics of waves and some calculations involving energy and frequency and wavelength. But we need to move on to quantum mechanics, which deals also electron configurations. So what you're trying to do for quantum mechanics is tell the exact location of an electron. You're like the GPS system for the electron. Which city it's in, which street it's in, how many feet away from the building, whatever. All the specifics. This is what the quantum mechanics does. These quantum numbers, which is a system of letters and numbers, ironically, it tells you exactly where the electron is located. Good news, you don't have to know all the quantum numbers part. There's a whole system for that, but they don't really touch you on it. You just need to know how to use the letter system predominantly. Okay, your first quantum number is your shell. Your shell can be 1 through 7. Technically, it could be 1 through infinity because anything's possible, right? So what does that principal quantum number tell you which shell it is? So if I tell you 4s, I'm telling you an electron in the 4th shell. The s, we'll talk about what that represents in a second. Higher the shell number, the more energy the electron has. Extremely important. Please remember this. Why is it easier to remove an electron from the 5th shell than the 1st shell? The 5th shell electron has more energy already inside of it, so you need to put less to get it out. Whereas the first shell is really close to the nucleus, has great attraction, it's hard to remove. And we'll talk about ionization energy a little later. But I want you to understand, this is very important, the bigger the shell number, the bigger number you see for that first value, the further it is from the nucleus and the more energy it has. Number of electrons, if you want to calculate how many electrons a specific shell can hold, let's say I tell you it's 4s. You're like, you know what? How many electrons can the fourth shell hold? How do you do that? Really simple. You square the number first, then multiply by 2. Please don't do 2 times 4 and then square it. That's just bad math. So 4 squared is 16. So I just plug it into this formula, 4 squared, and then multiply times 2. So I get a total of 32 electrons. So the fourth shell can hold a total of 32 electrons. You can do this for any of the shells. All you have to do is just plug in the shell number here, squared, multiply by 2. That's how many electrons can be there. All right, subshell is basically what's the general region electrons found. So these are the different types of shapes you're looking at, different regions. So if you have an S subshell, it tells you that the electron is located somewhere in a sphere. Obviously, the bigger the number, 2s, 3s, the bigger the sphere. That's all that second quantum number does. It tells you what's the general region. So you could find this electron somewhere in the sphere, somewhere in the sphere, somewhere in the sphere. If it's a P subshell, which is the other, so you have 4 different letters that could be represented by that second quantum number. So your first quantum number, remember, is the shell. The second tells you your subshell. And what is your subshell? Basically, where the electron can be found. Like for P, it can be found either in the Z, the Y, Z, X, or Y axis. So Z has 3 different possibilities. So you can find this electron either somewhere here, here, or here. That's what the subshell tells you. So when you see P, that's what it really means. Now, do you really need to sit there and overanalyze? No, you don't. I just want you to understand what the heck it is. And all it is basically, what's the region of electrons? Are you going to find the Z-axis, the Y-axis, the X-axis? That's what this information tells you. D is even funnier. Look at this. These are your possibilities. It could be in, if you have it, the first electron could be here, could be here, 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 here. The different possibilities. Because it's so weird, you don't have to sit there and memorize all these shapes or anything. I just want you to understand where it's coming from. But that's what it basically is. So the second quantum number tells you. So if I tell you 4s, I'm telling you it's in a fourth shell, and the electron is somewhere in the sphere. If I tell you 4p, I'm telling you it's in a fourth shell, and it's in one of these possibilities. The electron's either on this axis, or this axis. Which one is not really important right now? So that takes us to the third quantum number. Describes whether the orbitals on the X, Y, or Z axis. So now that we have identified there's 3 possibilities, like for P, for S there's only one axis, right? So if you look at it, there's only a single axis. This is all you got, somewhere in the sphere. The P, you have 3 different possibilities. You could have it on the Z, the Z, the X, or the Y. For D, you could have it here, 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 here. So what this third quantum number tells you is which one is it. So second one tells you, you know, what the possibilities are. So if you see P, you're like, okay, it's 3 different possibilities. It could be X, Y, or Z axis. What does the third quantum number tell you? Which one it is. That's what this orbital is. So orbitals are based on which subshell the electrons locate. So S subshell is only one orbital. So S, and the way we're going to represent this without doing those crazy drawings, S is just going to have a single subshell. So we represent it by a line. Then we'll put electrons above it. There's another system of electron configuration we'll talk about in a second. But I just want you to understand, for now, let's visualize it. So the electrons for S are going to be located here in this one orbital. For P, you have 3 orbitals. So how are we going to represent 3 orbitals? 1, 2, 3 lines. So the electron is going to be there in this, this, this. We'll call this X, Y, Z. You don't need to do that. Yeah, just you don't have to. I just want you to understand that's what it represents. But please don't sit there in electron configuration write X, Y, and Z. It's not worth it. D subshell has 5 orbitals. So how do I represent 5 orbitals? 1, 2, 3, 4, 5. F has 7 orbitals. 1, 2, 3, 4, 5, 6, 7. So now we're getting to which orbital is the electron. Is it here? And the way we're going to represent orbitals, by the way, is like this. A little half arrow. So is it located here? You know, how many electrons do you have here? This is 3, 4, 5. This gets to the 7. Gets interesting. We'll come back to this orbital diagram stuff, which is what this is, by the way, in a second. Each orbital can contain a maximum of 2 electrons. So how do you show a second electron in the same orbital? Well, You can't have them looking like this, so you actually have one going this way. That's where the second electron will be. All right, and then your last quantum number is your spin. So your spin has two options. Either it's going to be facing up or it's going to be facing down. So you are able to tell which shell the electron's in, what's the general subshell, right? Which type of path that's possible for that electron, which orbital, so is it on the x, y, or z axis? And then you could tell if it's facing up or down. That's what those four quantum numbers does. It tells you all that information. So to describe whether you have a positive or negative spin. So the first electron, just FYI, has a positive spin. The next one has a low spin or negative spin. So rules to be aware of. One, Pauli exclusion principle says no two electrons can have the same spin in a single orbital. Impossible. So don't do it. Hund's rule says that all orbitals in a subshell must be occupied with a positive spin electron before one with a negative spin can occur. What does all this mean in English? So let's say you have P, right? P has 3 orbitals. What this first law tells you is that you cannot do this. That's a big no-no. They can't face each other, ever. So when you do that, you are contradicting Pauli exclusion principle. That's all Pauli is telling you. They can't have the same spin, whether it's both facing up or both facing down. You cannot do that. So Pauli tells you that's a no-no. Hund, on the other hand, said, you know what? Let's say you have these 3 orbitals. Let's say we have a total of 4 electrons that are possible for this subshell, theoretically. What Hund said is that you cannot do this. You cannot fill a negative one before a positive, and let's try a different example of it, because the way you see aesthetically this is legal now, but the way I filled it was illegal. I couldn't do up down first. Let's say we have a total of 3 electrons instead. So 1, what Hund said, you cannot do this. You cannot occupy a orbital with a negative spin until all the orbitals are occupied. So no negative spins are possible until all 3 of these are occupied. So if I only have 2 electrons, that's how I have to draw them. You cannot do, you cannot do this. Big no-no. Can't do it. All the orbitals have to be occupied before anything has a negative spin. So be aware of that. All right, so let's try some questions. How many electrons can a potential level n equals 4 hold? So remember the formula, n squared. So 4 squared times 2, which gives me 32. So that's your answer. How many electrons can potential level 3 hold? Same thing, 2 times 3 squared, 9, 18. Number of electrons in a p orbital. So how many can p hold? Well, any orbital has a maximum of 1 or 2. You could have 1 up, 1 down. It said orbital. It didn't say subshell. If it said subshell, then technically you could hold a total of 6 electrons, right? Because 2 per orbital, there's 3 orbitals. But in this situation, it just said a single orbital. So be careful with the wording. Subshell and orbital, 2 different words. Subshell refers to all 3 orbitals. Orbital just refers to 1. Whether you say d orbital, p orbital, or s orbital, that's only 1 single location, and that could be a maximum of 1 or 2. Number of electrons in a p subshell. Well, how many orbitals do you have? 1, 2, 3. Simple memorization. Number of orbitals in a 4d subshell. Remember d. The 4 is irrelevant. The d is what you use for determining how many orbitals. There's a total of 5 for d. A number of electrons in a 3d subshell is the maximum. Which orbital can hold 2? You have 5 orbitals. 5 times 2 is 10. All right, so now we get to the part of electron configuration. How do you draw electron configurations? The way we're going to draw electron configurations is by using the periodic table. So, for example, this is fluorine, this is chlorine, this is argon, this is neon. So let's try a couple electron configurations. Actually, let's not do argon. I don't want to do that. Let's do zinc. So let's say, for example, you want to do electron configuration for fluorine. You just follow the periodic table. So 1s, 2. The first 2 electrons for this element, so it has a total 9 electrons. What you're trying to do is locate those 9 electrons. Where the heck are they? So how do you do that? You fill it from lowest energy to highest energy. Lowest energy is 1s. What's next in terms of energy? 2s. What's after that? 2p, 3s, 3p, 4s, 3d, 4p, and so on. That's the way this works. So all you're going to basically do is use the periodic table and follow along from left to right. Understanding that your D is going to be 1 less than your period number. So D starts in the 4th period. So 1 less than the period number means 3. So D starts with 3D, not with 4D. You don't go 4S, 4D. I know what you're asking. Why the heck is this happening? It turns out that the 3D electron has more energy than the 4S electron, even though the 3D electrons are in the 3rd shell. So if you have this your nucleus, right? 1, 2, 3. For some really strange, and here's our 4th shell, this 3D electron here has more energy than an electron located further away. Makes no sense, but that's the way it is. That's all this is telling you. This is still in the 3rd shell. I want to make that clear. 3D is still in the 3rd shell. It's not in the 4th shell. It's not a valence electron. 4s is your valence electrons. But because your 3D electron, for whatever strange reason, has more energy than the 4s, we draw electron configuration that way. Remember, it's lowest energy to highest energy. The other thing you want to notice, these 2 down here are members of period 6 and 7. They're pulled out. Why? To make the periodic table more condensed, so you could easier see it. You could see it more easily. So the way this works, after 6s, you don't do 5d, you do 4f. Because the ones before these 5d electrons are the 4f electrons. If you look at the periodic table, you see what I'm talking about. So you would actually go 4f, you go 6s2, 4f14, and then you go 5d10, and then after 5d10, 6p6. So it's extremely important you use this to help you figure out the periodic table. It's a really easy system. First 2 groups are your s blocks. These at the end are your p blocks, and the p blocks are basically going to follow the period number. So if you're like, what's this one over here? Well, it's in the 5th period. It's in a p block, so it's a 5p electron. This is your d block. And remember, your d block is one that's your period number. So this element, whatever it is, the zinc, is in the 4th period, right? So where's the electron located? Well, it's located in 3d. Why 3d? Because that's the way the system works. Same thing with down here. So just be aware of that. So let's get back to this. We're going to follow from lowest energy to highest energy. So 1s2, 2s2. Look, I'm just following along. Then comes 2p. And where's my stop sign? P1, P2, P3, P4, P5. Notice 5, 7, 9 electrons. That's the electron configuration for fluorine. So if you're asked to draw electron configuration for fluorine, this is all you would do. Now, if you want to do the orbital diagram, theoretically, so it'll be 1s, right? Here's your 2 electrons. Then you have 2s, remember 1 orbital. There's your 2 electrons. And then 2p, remember p has 3 orbitals. So 1, 2, 3, 4, 5. That's the orbital diagram. If you want to do it for fluorine, that's what it'll look like. All right, so let's try another one. Let's try chlorine. So chlorine, same thing. We start with 1s2. The way this works, you fill it up in order. So 1s gets filled, and how do you fill it? By putting a 2 there. Then 2s gets filled. How do you fill that? By putting 2, because that's the maximum that particular orbital can hold, that subshell can hold. Then you need to go through 2p, right? So we're going to go 2p6, so we need to fill all of them out. Then we go to 3s2. Look, all I'm doing is follow the periodic table, and you go all the way here to 3p5. So that's chlorine. Now, what if you want to do neon? Well, neon is really easy. Just go 1s2, same as I've always done. It's the same pattern every time. It doesn't change. And then 2p6 because it's on 1, 2, 3, 4, 5, 6, in the 6th location. That's how the system works. And then your last one, your zinc. My stop sign is going to be 3d10 because that's what it is. It's 1, 2, 3, 4, 5, 6, 7, all the way to 10. That's where I stop. So I'm going to keep on going from left to right until I get to my stop sign. So I'm going to go 1s2, 2s2, 2p6, 3s2, 3p6. All I'm doing is just following the periodic table left to right. Then comes 4s2 and 3d10. And there's your electron configuration. So that's how you use the periodic table to do electron configurations. So the first one, remember the first value represents your shell. Your second value represents your subshell. And those exponents basically tell you how many electrons are located there. Now, when you add them all these together, you should end up with the electron configuration for the element. It should match the number of electrons. So you could count 6, 8, 10. You look in the periodic table, what neutral atom has 10 electrons? Neon. So for hydrogen, it's 1s1, helium 1s2, lithium 1s2, 2s1, carbon 1s2, 2s2, 2p2. Notice 6 matches the atomic number, which is the number of electrons because the atom is neutral. Sulfur, go all the way to 3p4. All right, so let's try some more. Chlorine we already did. So remember, it's 1s2. So you're going to look in the periodic table for chlorine. You're like, okay, it's in the 3p5. It's going to be the stop sign. So you're going to keep on filling until you get to 3p5, and you're done. So maybe that's the easy way of looking at it. So figure out what your stop sign is, and then just go left to right in the periodic table until you get to the stop sign, and you're done. So like for strontium, where is it at? You look to see where its stop sign is, which turns out to be 5s2. So you're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Stop sign, you're done. To verify you're correct, if you add them all together, you get the atomic number for strontium. And for iodine, where's the stop sign? I believe that's like 5p5. So you're going to keep on going until you get to 5p5. Notice we went through the 1s2, 2s2, 2p, 3s, 4s, 3d, 4p, 5s, 4d, and then finally 5p5, and you're done. That's how you draw electron configurations. Orbital diagrams, all you're doing differently is you're showing arrows instead of exponents. So you can see for lithium, 1s2, 2s1 looks like that. Beryllium, 1s2, 2s2. Boron, now you have an up arrow. Notice how it's abiding by Pauli exclusion principle, not showing two up arrows in the same orbital. You also see that it's filling in order, so it's putting an electron by itself first before it pairs it up. And then carbon, nitrogen, oxygen. So the only thing you really have to pay attention to is make sure your first arrow is up, second one's down, and you're good to go. That's how you do orbital diagrams. So these are useful if you want to know how many electrons are spin paired. Like in this situation, none of the p electrons are spin paired, but the s electrons are. Spin paired means both electrons are in the orbital. So it's occupied. You have an up and a down arrow. That's spin paired. This is spin paired, so you have one set of electrons spin paired. Here you have two sets. There's 2 here that are not spin paired, 3 here not spin paired, 1 here is not spin paired. We'll come back to what that means later. And here's later. So what spin pairing does is it determines if you're paramagnetic or diamagnetic. So if your electrons are not all spin paired, like these are all spin paired, right? So these are diamagnetic. This is not spin paired. Paramagnetic, 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 diamagnetic, because all the electrons are spin paired. So what's a shortcut for all this? Any element that ends at S2, P6, D10, or F14 is all spin paired, which means diamagnetic. Everything else is paramagnetic. What the heck is pair and di, you ask? Well, let's look at it. Diamagnetic is used to determine if elements have all electrons spin paired and if metals are attracted to magnets. So that's what diamagnetic and paramagnetic are for. There's something going to get attracted to a magnet if it's a metal. Basic elements ending in S2, P6, D10, F14 are all spin paired and thus are not going to get attracted to magnets. Diamagnetic, no magnets. Magnets will not work, and if it's a metal anyways. Paramagnetic, on the other hand, is that something that will attract a magnet. So if you look in your periodic table, for example, you'll notice that zinc is D10. That's diamagnetic. Magnet's not going to work on it. Iron, on the other hand, is magnetic because it's paramagnetic, right? Not all the electrons are spin paired. You have basically D6. Why is that important? Guess what your coins are made out of? That's right, zinc. And guess what zinc is not able to do is work on a magnet. So you can't use a magnet on a vending machine, for example, to pull the coins out and get the money back. Sorry, it's not going to work. cool if you could. You would need something like iron. That's why they don't use iron. Besides the fact that rust, it's also because it's magnetic, so it's not going to really be advantageous for money. Electron configuration concepts you need to be aware of. Ground state means electrons are written from lowest to highest energy. So what we've been doing is called the ground state. That's all that is. So that's the ground state configuration. Excited state means something's out of sequence. So instead of seeing all the electrons fill in the order they're supposed to, something's going to be out of sequence. What happened here for nitrogen, we took a p electron, jumped it to the next shell. It could be the 3p, it could be the 3s, it could be 4, 5, 6, it doesn't really matter. The way you could always tell excited is that it's got the correct number of electrons for that element, but they're not filled in order. That's the only thing you need to pay attention to. Cations. Whenever you make a cation, you take electrons from the valence shell. That's a shell furthest from the nucleus. Why do I make a big thing about that? Fe2+, if you look at Fe, your electron configuration to the ending will be 3p6, 4s2, 3d6. So when I show this to students, usually like 2+, okay, you take 2 electrons out because it's a positive 2 charge. They'll take it from the 3d subshell. You cannot do that. Do not take it from 3d because in a third shell, that is not your valence electron. Your valence electron's the 4s. So why did this look like this? Why is the 4s going poof? Because that's where you moved your electrons from. So remember, when you're ever taking electrons out to make a cation, always take it from the last numeric shell. Anions, on the other hand, you're going to add electrons. So where do you add it? The last numeric shell again. And in these situations, when you get anions, you will get a complete shell as a result of it. So you always end in P6 for any anion. That's just the way it's going to happen. Because the whole point of getting a negative charge is to get a complete shell. So nitrogen with a negative 3 charge would be P6. Oxygen with a negative 2 charge, P6. Fluorine with a negative 1 charge, P6. That's just the way it always is going to happen. So be aware of that. Some anomalies. Elements in group 6 and 11 have unique configurations. Elements in group 6, which is right here, and in S1D5. You would think it'd be 4s2, 3d4, but that's not what happens. The reason is that it's more stable for a subshell to be half filled than partially filled. So by doing, in this situation, you're going to get S1, D5. You're half filling both of these. That's more stable than doing S2 and D4. So everything in this group is going to follow this rule. It's going to be S1, D5 ascending. So if you do, like for this one, 1, 2, 3, 4, 5, 5, like for this one, molybdenum. If you do 5s2, 4d4, you'll be wrong. You would have to do 5s1, 4d5. Otherwise, it's the wrong answer. And same thing with this group. This thing does this S1, D10 thing. So everything in this group is going to end in S1 and D10. That includes silver and gold. So be aware of that. Those are the only 2 anomalies, and they do come up from time to time in questions. So when you ask the question about them, make sure you're aware of that. All right, basic rules of periodic trends, which is the next thing we're going to go over. Protons attract electrons. Really simple. Opposites attract. Things you need to be aware of. Regards to that, the closer electron is, the greater attraction. So electrons in the first shell have greater attraction than electrons in the 5th shell. Common sense. The closer it is, the more attraction. More protons means stronger attraction. This is mainly applicable if you're talking about elements that have the same number of shells. So if elements in period 3, the more protons you have, the greater attraction you have toward electrons. If you're comparing 3 to 4, period 3 and period 4, that's not really the same, right? Because period 3 has 3 shells, period 4 has 4 shells, so the proton's not going to be as big of a deal. But if you're talking about elements in the same period, protons are the only deal. And electrons shield electrons from the nucleus, so more shells means less attraction. So as you add more shells, you have what's called shielding, which in English means that these electrons here in this 3rd shell or 2nd shell will shield the nucleus, block it basically, from these electrons in the outermost shell. And that means there's going to be less attraction to them. So that's what shielding basically is. The more shells you have, the more shielding, because there's more chance for electrons in the closer shells to block ones from the further shells. And complete shells are so stable, so results of gaining and losing electrons usually to complete a shell. That's usually the byproduct. It's not necessarily the cause. I mean, realistically, it's like the atoms out there saying, oh, I need to get a complete shell. But if it's going to lose and gain electrons, it's going to make sure it gets a complete shell because it's more stable. So with those rules in mind, we're going to go over the trends. First, the radius. Distance from the nucleus to valence electrons. Remember, valence electrons are electrons furthest from the nucleus. More protons equals smaller size. So if you're comparing elements in the same period, more protons, same size. Why? Because when you go, like let's say the second period, this is your nucleus, this is your first shell, this is your second shell. All your electrons are being added to this exact shell. So what's going to determine how attracted they are to the nucleus? The number of protons. The more protons you have, the closer they are going to be to the nucleus and the smaller the size. So in a nutshell, this means that your size decreases as you go to the right. Your atom gets smaller. And the reason is protons. Please do not say because the trend increases or decreases to whatever direction. That's not the answer. You have to use protons. If you're explaining any of these trends for elements in the same period, PP, protons, period, protons, protons. You have to do that. You have to use protons for justification. You can also use effective nuclear charge if you really aren't into it, but at least protons. Otherwise, you can be marked wrong. More shells in groups, bigger size. Common sense, right? You see even in my diagram, the more rings you draw, the bigger the atom gets. Common sense. Ionic radius, I know what you're saying. What, is it the same atomic radius? No. Atomic radius is for a neutral atom. Ionic radius is for an ion. And there's two kinds. There's cation and there's anion. Cations are smaller. Why? Well, let's look at lithium. Right, lithium has a nucleus. It's got 1, 2, 3 electrons, a neutral atom, right? But you make it a positive charge. You make a cation. You lose this electron. Guess what? Now you only have one shell. Your atom just shrunk to half its original size. That's why cations are smaller. They lose a whole shell. And as a byproduct, guess what it gets? A complete shell underneath. So cations and anions, except for transition metals, are a little weird. When you're talking about the group 1 and 2 and then 3A through 8A, when they gain and lose electrons, the result is usually getting a complete shell. Not 8A, because noble gas, they already have a complete shell. But groups 3A through 7A, that's the whole thing, right? They get a complete shell. The metals, which are on the left side, or the cations, which what they usually form, are lazy. They are able to get a complete shell by losing electrons, not gaining. There's no work involved. Anions get bigger. And I know what you're saying. Why the heck does it get bigger? Let's look at oxygen, which has 8 protons, right? So here's your first 2 electrons. Then you have 1, 2, 3, 4, 5, 6. That's what oxygen has. So you have 2 more electrons because oxygen gets a -2 charge, right? So what happens? You add it here. Here's the thing. Electrons hate each other. They repel the heck out of each other. So when you add these 2 electrons, they repel the rest of the electrons on the same shell because they're all in the same shell, right? So what happens? The atom doubles in size. So what's your explanation? When you form an anion, you increase electron repulsion, which is a fancy of saying electrons don't look like each other. As a result, the atom gets bigger in size, double the size. Just like cations get half the size, anions go double the size. Interesting little fun fact. But that's the reason, because of that. Now, if you're comparing a cation to an anion, it gets a little more complicated because you have to count how many protons it has and then see if they're isoelectronic. Isoelectronic means they have the same number of electrons. So oxygen is this. Let's say we have, so when you get this, you have 10 electrons. So that's neon's configuration. Let's say we do sodium. Sodium would look exactly like this. So this is oxide, but this is also Na+. Because when sodium loses an electron, it gets a complete shell like this by losing its 1/3 shell electron. Now, why do I want to point that out? Which one of these is smaller, the sodium or the oxide? Now, these are isoelectronic because they have the same number of electrons. That's a common comparison. You're going to see that a lot. How do you know which one's bigger? Count your protons. Because they have the same number of electrons, so you can't use that as your basis. Same number of shells, can't use that. This has a total of 8 protons. This has a total of 11 protons. Guess which one's smaller? That's right, sodium. more protons, smaller size. So when the atom is isoelectronic, even if they're in different groups, different periods in the periodic table, you can figure out which one's smaller by looking at your protons. That's about the only time it counts. Ionization energy, the energy you need to remove an electron, can be the first, second, or third ionization energy. It gets really cute. More attraction to electrons, the greater the value. So this basically is telling you that the smaller it is, the greater the ionization energy, right? Because the smaller it is, the greater attraction to its electrons. Because if you're looking at almost the same period, as you go to the right, what do? You add more protons, more attraction, which means higher ionization energy. So this is the opposite of size. As the atom gets smaller, going to the right, ionization energy gets bigger. Harder to remove an electron because the electron is close to the nucleus, so it's more attracted to it. You need to put more in. Electronegativity, on the other hand, attraction of an atom to electrons. Cuteness factor, how cute the atom is. So, noble gases are all zeros. They're all ugly. They have complete shells. There's no reason for them to attract electrons. Please remember that. They have zero electronegativity. The rest of the elements, same trend as ionization energy. So that means your electronegativity increases as you go to the right and as you go up a group. Because as you go down a group, what happens? The atom gets bigger. And the bigger it is, the less attraction to electrons, the lower the ionization energy, the lower electronegativity. But as you go up, less shells, smaller size means more attraction. More attraction means higher ionization energy, high electronegativity. So noble gases have zero because they're not attractive. All right, amount your electrons have. Energy depends on how far the element is from the nucleus. The further it is, the more energy it has. Please remember that. So the trend for ionization usually is as you go to the right, it gets bigger, right? And look at this. This is ionization energy. This is showing you that lithium is 500. In case you didn't notice, these are elements in the same period. So this is beryllium. This is boron. This is carbon. This is oxygen. This is nitrogen. And what you'll see here, you see how the ionization energy decreases between beryllium and boron? That shouldn't be happening. Boron has more protons. It has 3 protons to beryllium's 2. There should be greater attraction, but that's not what's happening. So what the heck is going on? That's when the anomalies come in. That's what we have to pay attention to. So we're going to discuss what that is. So electrons in a p orbital have more energy than electrons than the s. This electron configuration for beryllium, this is for boron. So when you move the first electron for boron, you're moving it from here, the p electron. And we said the p electron has more energy. So because it has more energy, you need to put less in to get it out. The more energy an electron has, the less energy you need to put to get it out. It's kind of like who's going to be more likely to go outside and play with you? Someone that sits on a couch all day and has low energy, or someone that does exercise all day? Person that does exercise all day, right? Because they have more energy to begin with. Same principle here. So the p electron is easier to remove than the 2s electron. It's not because of complete shell. Don't make a silly argument like that. It's based on where it's removed from. So it turns out that for every member of 2a versus 3a, this holds true. That the ionization energy actually goes down. So this is 3a, 2a, 3a. So and the reason for it, and the reason you can explain it, because the p electron has more energy and thus has a lower requirement of energy to remove than the s electron. So removing 2 p electrons from B takes less energy than removing 2 electrons from B. Another easy way to put it. That holds true for anything between 2A and 3A. Please remember that. The other possibility is nitrogen versus oxygen. So I'm just going to draw the p electron for it just so you could see. So this is the one for nitrogen. This is the one for oxygen. The only difference is this one's been paired. So you're like, whoa, whoop-de-doo, what's the big deal? Remember what we said earlier? Half-filled is more stable. So this is more stable than this is. What's the significance? Look at the ionization energy between these two. Nitrogen actually has a lower oxygen has a lower ionization energy than nitrogen. The reason for it is because nitrogen has a half-filled subshell, which is more stable. So that's why it drops. Because ordinarily, what you expect it to be, instead of doing this little thing like this, it should be going like this. So this is the reason. This is for any elements in period 5A versus 6a. This theory holds true. So N requires more energy to remove its electron because it's half filled. I should have said that. Because it has a half filled subshell. Come on. Subshell, which is more stable. So those are your anomalies. Otherwise, the trend matches the periodic table in terms of more protons means more attraction. These are the only anomalies. So now let's look at second and third ionization energy. So sodium has a first and a second ionization energy. Everything does. What is the point of this? You're going to focus on energy of the electron being removed, which is based on its location, right? So why the heck does this electron require 10 times the energy of this electron? What the heck? How does that make any sense? Where's it being removed from? For sodium, this is removed from 3s1. For the second electron, 2p6. Guess which one has less energy? The 2p electrons have less energy, so you need more energy to remove them because they're closer to the nucleus. So your reason for this is that the electron is closer to the nucleus, or you can just point out where it's removed from. The second electron is removed from 2p6, first one is removed from 3s1. Thus, the 2p6 electron has a greater energy requirement because it's lower energy. So in the same shell, electrons in S requires more energy than those in P. If you're talking about different shells, then the lower shell requires way more energy than the higher shells. The significance of this is really important because you can actually tell, like I could completely block all this off, like don't pretend like you don't see these. And you could actually figure out which group the element's from. And the reason you could tell that is by looking at the energies. Okay, 7 to double, okay, not bad. Whoa, crap, what happened there? 7-time increase. Wherever the biggest jump is, that's the one that's removed from the shell underneath. So this is telling you these two want to happen. This third one does not want to happen. Why? This is removing an electron from a complete shell. Why is that important? This tells you the electrons, this is going to be the S electron, the S2 electron. This is the S1 electron. This is the P6 electron. So this is a group 2A element, based on the fact that jump is between the second and third ionization energies. Here, look, 5 to think, triple, not big deal. Little increase, not even double, and then boom, 5-fold increase. So the jump is between the third and the fourth, so this is a group 3A element. Wherever the jump is, that's how you can tell what group the element's from. Here, double, not a little bit increase, then boom. So between 4A and 5A, so this is a 4A element. You notice how it's based on the lower location. So this is 4A. This one, even without doing it, guess what it is? It's a 5A, because look where your jump is, between 5A and 6A. So you can actually identify the element group number based on this information. That's important to note. Our electronegativity, same period. Notice it goes up as you go to the right. Why does it increase? Because you're adding more protons. And that's all the way across. There is no anomaly like ionization. You notice this consistently goes up, up, up. There's no drop off like ionization energy between here and here. There's a drop off between Be and boron. Not happening with electronegativity. It's consistent. The only thing you need to know, the noble gases are all zeros. And as you go down, guess what happens to ionization energy? It goes down. Why? Atoms getting bigger, less attraction to its electrons. So that's why electronegativity decreases. There's more shielding too. That's not what we're looking at. Same group, more shells means greater shielding from nucleus and less electronegativity. Atomic radius, look what happens to the size. Ooh, 37 to 31, it shrunk. Why did it shrink? One more proton. Why is it shrinking? This has 2 protons. Excuse me, this has 4 protons, this has 3. This has 5, this has 4. That's why this is smaller. More protons, more. See, as you add more protons, what happens to the size? It gets smaller. Notice once again, no anomalies. You don't see it going from 77 to 80 and then going back to 73. It's consistent. Only thing that has the anomaly is ionization energy. And as you go down, what happens? Your size gets bigger. Why does it get bigger? More rings. So if you're trying to explain atomic radius in the same period, more protons equals smaller size. That's your explanation. different periods, the more shells an atom has, the larger its size. Common sense. All right, now we're going to go to PS, the last topic. This is a new topic introduced into AP exam. And what it's based on is this thing, which every high school in the world has, obviously, right? No, it doesn't. What this thing allows you to do, it allows you to identify an element. Like you could exactly figure out which element is in a sample using this kind of information. So we're going to go through it. It's basically connected to trends and it's connected to electron configuration. So these are different parts, and you're like, what do you do? Who cares? So how do we probe further into the atom? So energy equals HV, right? So if I want to see the molecule rotations, molecular rotations, I'll put microwaves in. So let's say you want to study an atom. In order to study its rotations, which is the lowest energy requirement, use microwaves. Microwaves, remember, is not high energy. It's actually weaker than visible light. If you want to see them vibrate, use infrared. If you want to cause them to move from one shell to the other, you can use Rho-G BIV, certain elements. That's enough energy to make them jump from one shell to the other. If you want to have them transition in atoms and molecules, maybe closer to nucleus electrons, use UV. And if you want them to affect the core electrons, which are non-valence electrons. So your valence electrons are your last ring, everything else is a core electron. So if you want to observe your core electrons, use X-ray. Why is this important? Well, here's why. I'm putting energy in, so that's a valence electron, right? Outermost shell. So for that one, what do you need energy-wise? Well, it turns out you need only about 495 kilojoules per mole, which is about 0.495. And you're like, who cares? Well, why does that matter? Look it up here. Which one of these has enough energy to remove? This is in megajoules per mole, by the way. Notice the one you would need to use to cause that transition of the valence electron would be at the very least ultraviolet. Now, if you want to see something, if you wanted it to be impacted by visible, that means the energy requirement had to be this. So by calculating the energy, you can figure out which exact type of energy you need in order to cause it to happen, whether you want it to rotate, vibrate, move from one shell to the other, whatever. It's based on the number, and these numbers tell you that. Now, notice that was a core electron, that was an electron in the first shell. So what do you think I'm going to need for that one? X-ray, obviously, right? Just the most energetic. Say there's your core electron. There's the energy requirement, 3 to 6 megajoules. And if you go back to the slow diagram, 3 to 6 megajoules, that's a pretty large number. You could possibly use ultraviolet, or you could use X-rays for that one, because 3 to 6 falls between 0.3 and 100, and also 10 to the second to 10 to the fifth theoretically. But for this one, UV would be enough. And by the way, X-ray can make all those other things happen. You could cause it to vibrate, to transition, do all that stuff. So it depends on what you're trying to study, what you're trying to analyze. What we want to do is none of this stuff, this vibration, all that stuff. What we want to do is identify the elements. So we're going to take this a step further and use the data. So this is the machine. You put either X-ray or UV source. You jump energy into it. That was a core electron. Notice, see that little bump that popped up right here? So the next one, you're moving another core electron. There's a bump here. That was a valence electron. Remember, it was right there. That was a core electron right there. It's just repeating itself more or less. And then next electron, once again, valence electron. So what this tells you is exactly how many electrons are in each location, each subshell. So the more energetic the electron is, the closer it is to the nucleus. So which one of these is representing the first core electron? Is this one, right? And that's why you're going to read these, by the way. The biggest number one, which is usually on the left. Sometimes they'll get cute and put on the right side the biggest number. Just fixate on the biggest number peak. Whatever your biggest number peak is, it is always going to be your 1s2. Always, without fail. It could be 1s1 if it's a really small peak, because remember, your S subshell can hold a maximum 2 electrons. For this one, this peak looks like 2 electrons. How do I know it's 2 electrons? Because you have this peak. You cannot have this peak until this one's filled. It's like electron configuration. You can't go, and for those of you that are probably thinking ahead, what comes after 1s2? Oh, 2s. So is this going to be a 2s1 or is it going to be 2s2? Well, look at the height. It's about half the height of this, right? We know this is 2 electrons, right? So 2 electrons is this height. So half of that height will represent 1 electron. So this is going to be 2s1. So we can actually identify this as being 1s2, 2s1. And if you look in the periodic table, that means this is lithium. That's what this PS data allows you to do. It allows you to figure out exactly which element you're looking at. Let's look at another one in case you're still not sure. So we do boron. Here's the energy. So shooting at 19.3 core electron, right? That's your what? That's guaranteed to be your 1s because it's the most energetic, right? So this is going to be 2s, maybe. We're going to see if there's anything in between just to make sure. So there's your 1s2. It filled. Once you see this extra peak, this had to have been occupied. There's no doubt about it. So let's see what's the next. Oh, so that means this is 2s2. Notice they're the same height, right? So this is 1s2, that's 2s2. Oh, looks like this was going to get a little bigger. There you go. That's the height. Sorry, I got ahead of myself. So this represents, what the heck? How high is it going to be? It's still 2 electrons, guys. No matter how high this darn thing gets, it's going to just be 2 electrons. The height of this tells you what the reference point is for an electron. So now they're identical. They could have just made it, 2 peaks and that's it, but they decided to get cute with this. So let me erase this real quick because that's a lot of lines and you're probably confused now. All right, so this is your reference point. This height represents 2 electrons. So half of this height represents 1 electron. That's what you want to do first. You want to identify as your 1s2 and then reference what the height is for 1 and 2 electrons. So this is 2 electrons. So this is 2s2, same height, right? So guess what this has to be? That's right. After 2s2, you get 2p1. So that's what this is. How do you know it's 1? The height. Well, this is terrible line drawing, but it's about 1. So this is how you know this is boron. So why does this one have so much energy requirement than this? This is a lower energy electron. So you need to put more in to get it out. Whereas the 2p, you put less energy in. Why does the 2p electron have a lower binding energy, which is what this referencing is? Because this 2p electron has more energy than the 2s electron. Remember, p is more energetic than the s electrons. So you need less energy to put it in, or take it out, excuse me. So this only requires 0.8. This requires 1.36. And the other one was lithium from earlier we saw. All right, so PS shows a set of peaks at different binding energies. That's what those numbers in the bottom represent, the binding energy. Each peak corresponds to a different shell and subshell, 1s2, 2, and you fill it in that order. So if you see 4 peaks, you can go 1s2, 2s2, 2p6, 3s. It's just going to always fill in that order, from lowest energy to highest energy. Don't ever change that. X-axis gives binding energy for different subshells, well, 1s electron always having the biggest value. Y-axis tells us the number of electrons in that subshell. So the height, which is called the intensity, is the number of electrons. And that's going to be either 2 electrons or 6. They don't really go D, so you don't see 10 electrons. So you're going to have 2 for S, or you're going to have 6 for P, because that's how many electrons are possible in S and P. All right, so X represents 1s2. Y, it's the most energetic. So what's next? This is 2s2. This is 2p6. Here's our reference point. Each line represents 1 electron. So 1, 2, 1, 2. This represents 1, 2, 3, 4, 5, 6. That's why it's 2p6. Then this is 3s2. And then 1, 2, 3, 4, 5. This is going to be 3p5. That's how you could identify it. It says 3p6 here, but this is 1, 2, 3, 4, 5. So it should have been 5, not 6. All right, analyzing data from PES. So where's our 1s? Right here. Just knock that out right out of the way. Pretty energetic, right? 84, 4.7. So he's a little further from the nucleus. Is going to be 2s2, then 2p. Okay, our reference point. Each line represents 1 electron. So 1, 2, 3, 4, 5, 6. 2p6, we know this is neon without even doing anything. So which element does this spectrum represent? Neon. We already figured that out because that's what it looks like. All right, next question. Given the spectrum above, identify the element in its electron configuration. So this is going to be 1s2, 2s2, 2p6. I don't even need to count because I can't fill this until these are all completely occupied, right? So it's 3s2, and then this one, we know each line represents one electron, so this is going to be just 3p1. So which one of these is it? Aluminum. All right, so let's try some more sample questions. Which element could be represented by the complete PS spectrum? We're going to do it ahead of time. You notice that they got cute in this? This is only 2 electrons, right? So guess what? This represents 1 electron. It's every 2 lines is 1 electron. That's why it's important you reference that first one, that first peak, to see what each electron is equivalent to. So this is also 2 electrons, so it's going to be 2s2, and then this is going to be 2p, 1, 2, 3. So which one of these does that match up with? Nitrogen. Which of the following best explains the relative positioning and intensity? So these are both 2s electrons, and that's important. Don't get cute. These are just both 2. This is not a situation where you're saying, oh, this is 1s, this is 1. That's not what this is about. They're telling you these are 2s peaks. So these are both 2s peaks. Okay, what's the question? Which of the following best explains the relative positioning? So B has a greater nuclear charge than lithium. Is that true? Yeah. Beryllium has a total of 4 protons, whereas lithium only has 3. So does that explain why the binding energy for beryllium is larger? Look, if you notice, between 10 and 12, whereas this is between 4 and 6. Yeah, that definitely does. Why? They're in the same period, and every time they're in the same period, it's nuclear charge or protons. They're kind of synonymous. Nuclear charge is based on protons, in case you forgot. So beryllium has a greater nuclear charge than lithium, and more electrons. So is that true? Well, Be has 2 electrons, right? Because it's a complete 2s subshell. So as 1, yeah, that makes sense. That's your answer. All right, given the photoelectron spectrum for the phosphorus and sulfur, which of the following best explains the 2p peak? 2p peak for sulfur is further to the left than the 2p peak for phosphorus. So let's first figure that out. 1s2, 2s2, 2p6, 3s2, 3p6. So we're looking for the 3p peak for that, and the 2p peak for phosphorus. So we're looking at this one. We'll fix in on this one first. Same thing here, 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so let's fix it on these. So you notice this one, it's further, or is this one further? Well, they're telling you, explains why the 2p peak of sulfur is further to the left. So sulfur is further to the left. Oh yeah, you could actually see it if you line them up, because they actually lined it up perfectly. Yeah, so this is further to the left. So why does this one have more energy required to move its electron? They're in the same period. So what's the same period always going to be? Nuclear charge protons. Nuclear charge protons. So S has a greater effective nuclear charge than phosphorus, true, and 3p sublevel, and S has a greater electron repulsions than sulfur. What the heck does this second part mean is what you're probably thinking, right? Each time you add an extra electron, you have greater repulsions between them. Greater repulsions between electrons mean greater distance. So that means the energy requirement is going to be different because of it. So that is the correct answer. The real reason is just that. The other stuff, obviously not great nuclear charge, great number of electrons, no, none of the other ones make sense. All right, number 4. So looking at the spectra for sodium and potassium, which of the following would explain the difference? So these are just 3s. These are both 3s. First off, why is this one shorter than this one? This is 3s for this. This is 3s for this. So you're like, well, why is this one higher? Look where potassium is compared to sodium. Sodium ends at 3s1. That is the ending. Potassium goes to 3s2, 4, 3s1, 1, 2, 3. Sodium is a 3s electron. Yep, sorry, that's a 3s1. This goes 3s2, 3p6, and then 4s1. So the last electron for both of them, because they're in the same group, are both in the 4s1. But you notice how this one has a complete filled s orbital because potassium had to go through it and complete it before it get to 4s. So that's the reason this is taller, because the 3s for this one's already complete for potassium, however for sodium it's not. So that explains the height part. But what about the energy? They're in the same family. So if it's the same family, what do we fixate on? Shells, 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 shells. So K has a greater nuclear charge than sodium. That's true. 10K has a greater nuclear charge, but remember different shells. If we're comparing 4s versus 3s, then that becomes a moot point because this one and this one are different distances apart, so nuclear charge won't matter. But what's the difference here? We're talking about only the 3s. We're not talking about the 4s. We're talking about the 3s for both of them. So can nuclear charge play a role? Most definitely. Yeah, because this has 19 protons for that 3s electron, whereas this has only 11 protons for that 3s electron. So that could definitely be it. K has more electronic repulsions than sodium. Yeah, it does. It does have more. Sodium has 1 valence electron in 3s subshell. Yeah, but that doesn't really matter. Sodium has electron shielding than potassium. Yeah, technically, but which one of these explains this situation? The nuclear charge. And for those wondering why can't it be the shielding, if it was the 4s versus 3s, yes, definitely shielding is your explanation. More shells, definitely. But we're only talking about the 3s electron, so shielding is out the door. We don't care about it because we're not comparing the valence shell anymore. We're comparing a specific subshell, and that's what makes the difference. And as far as potassium has more electron repulsion, absolutely true, but that's mainly going to be involved if you're talking about the 4s again. You're only talking about the 3s's, so that's not relevant. All right, looking at the spectrum for sodium and potassium, which of the following would best explain the difference in signal intensity? Why is one taller than the other? Why is potassium taller than sodium? We already answered this, ironically, because sodium has 1 valence electron and 3s, and what does potassium have? It has 2 s electrons, whereas potassium only has 1 in that location. And the last question, given the full electron spectrum of scandium below, which of the following best explains why scandium commonly takes positive 3 charge and ion to positive 2? Removing 3 electrons releases more energy than removing 2 electrons. Sounds interesting. Theoretically, it should require more energy, but we don't know if that's true. Scandium is in group 3, and atoms only lose the number of electrons that will result in a noble gas configuration. That's not true. Not in a general sense. The amount of energy required to move an electron from the 3D subshell is close to that of the 4s. That is absolutely true. They're very close in energy. 3D is going to be slightly high energy, but they're very close to each other. But significantly more energy is needed to move electrons from 3p subshell. That's absolutely true. Removing 2 electrons alleviates the spin pairing repulsions in the 4s sublevel, so does energy favorable. I mean, that just sounds like a bunch of gibberish. So the correct answer for this one, because you're looking at that, is C. So the one that made the most sense when we're reading through it, the amount of energy required to move an electron from 3D sublevel is closer to the 4s sublevel. Absolutely true. But significantly more energy is needed. Because the question is, which of the following explains why scandium forms a positive 3 rather than positive 2? And that's because of this explanation. Let's see. We don't want to spend too much time with this, but just so you can see the different energy requirements, you can see 1s electron versus 2s, 2p, the different energy requirements. And we talked about how ionization energy depends on where the electrons are moved from. So this electron and this electron, this one requires less energy than this one because P has more energy itself than the S electron, so that's why the energy requirement to move it is less. But when you're comparing S with P, huge difference. And the reason for the huge difference is this is much closer to nucleus, and you can see the binary energy kind of supports that. All right, mass spectrometry. We're going to talk about mass spectrometry and also spectrophotometry together. All right, mass spectrometer is basically an instrument that analyzes an element samples and identifies all its isotopes. That's basically all it does. Used to determine the mass of atoms. So zirconium has 1, 2, 3, 4, 5 different isotopes. So that's what mass spectrometry allows you to do, is figure out all the isotopes. What's the most abundant one? This one is. What's the mass of this substance, whatever it is? Notice that the majority of the mass is centered around this, percentage-wise. That's like 50, 60, plus 20. So about 80% of your mass is due to these three. So you expect, because the way the mass in the periodic table is determined, you multiply the mass times the percent abundance for each one and add them all together. So the one that's the most abundant is going to have the most influence on the mass. Your mass is going to be somewhere between 90 and 92 for sure. And that's what this other piece of information gives you. It tells you all the different isotopes. So it tells you that the biggest mass isotope is this one, right? Because it's got the biggest number. They all have the same number of protons. So the one has the biggest number, also has the biggest number of neutrons, in case you didn't know that. And how many isotopes do we have? 1, 2, 3, 4, 5. That's all the data you can really surmise from this. Please don't go beyond that in terms of what this thing can do. It can show different isotopes and different samples. So for copper, copper 63 makes up 69% of the actual mass. This makes 31%. So you expect the mass to be somewhere here. Why? Because this is the majority. If it was exactly 50-50, you expect it to be right here, but it's not. The majority is coming from this one, so you expect the mass to be a little closer. So probably 63.4, 5, something like that. And you could check down the periodic table. There are 2 isotopes of copper. You can also determine from here. And you could tell also that the one that has the most neutrons is this one. That's all the data you can really gather. All right, let's try some questions. Based on a mass spectrometry of Y, which of the following statements is false? Peak A and D come from atoms that have the same number of electrons. So this is saying which is false. Well, these are all neutral atoms, so yeah, they have the same number of protons. All these have the same protons, by the way. They have to. That's what definition of isotopes are. So they should also have the same number of electrons, right? That's true. We'll come back to this because it could be that the question is trying to draw our attention to something else, but we'll come back. There are 7 isotopes of Y. 1, 2, 3, 4, 5, 6, 7. That's definitely the case, so that's out. Peak C comes from the most abundant isotope of Y. Yeah, highest number. Peak D comes from an atom with 4 more protons. Oh, that's a big no-no. 4 more protons, that makes a different element. This is our answer. So A, which, if the reason I didn't completely eliminate it is that you can't really tell the number of electrons based on this information. You could kind of infer it, but it's not direct information. So if I didn't have D as a possibility, if there's something else, then A would have been the most logical one that was false. So that's why I didn't eliminate it right away. But in this situation, D made the most sense because they can't have different number of protons. 2, the identity of compound Y is, well, where's Y located? If you looked in the periodic table, you want to have, let's say, the majority of the mass is coming from here. So it's definitely not 99 and 100. That's definitely no. It's not anywhere near that. So then we look in the periodic table and we're like, okay, which one of these does it match up most with? So if you look at your periodic table, and I'll give you a second to do so, I can actually pull one up right now so you can see one. I think that'll make the most sense. Let's see, do I have? Let's get one real quick. All right, so we're going to escape out of here for a sec. All right, we're going to look at the periodic table. So let's pull one up. All right, so it's not going to be over 90 for sure. So if you look in your periodic table, based on the mass options, and this was a really bad one I pulled up. Let me pull a better one. Gives you better numbers, even bigger. Okay, so if you go back to the PowerPoint, the identity of the compound Y is, so we know the mass is not going to be over 97 for sure. So it's going to be somewhere between 92 and 97. So can we narrow it down between that? So between 92 and 97 mass-wise, and it looks like I picked one that has really small numbers that I can't even read. Okay, so 92, 97, so it can't be zirconium because it's 91.2. Niobium, it's 92.906. Not, I mean, it's going to be 92, 97, but it's not going to be exactly that close to 92. So the one that makes the most sense looks like a molybdenum. Because molybdenum, if you looked in the periodic table, is somewhere between 92 and 97. The reason I guessed it, because the majority of the mass is coming from these 1, 2, 3, 4, 5 substances. That's the reason I went that route. And which peak comes from an atom with the greatest number of neutrons? The one that's the biggest mass, so it's D. So that's how you would figure that out. All right, the other topic we're going to go over is spectrometry, spectrophotometry to be exact. So we're going to talk about Beer's law, and what basically this principle is, you have a light source, and this is what a spectrophotometer does. It shines light through this lens, and then it shines it through your solution. Now, what this does, it gives you what's called an absorbance value. Absorbance is how much of this light got absorbed through it. And the way it measures it, it knows how much you went through from this end, and knows how much it got to this end, and from that I can tell you the absorbance. Now, the important thing about this is that there's an inverse relationship between the amount that is absorbed and the amount that's transmitted. So the more that's transmitted, the less is absorbed, right? Because if a large amount of the light went through, that means most of the light went through, there's very little of it that got absorbed by the solution. What makes it get absorbed? Something inside there, chemical particles that are colored. And that's very important to note about this. You can't do spectrophotometry for a substance that is clear. It has to be colored. That's the requirement. If you have a colored solution, you can actually figure out the concentration of it using absorbance data. That's what this whole situation allows you to do. So a specific wavelength enters the sample and is absorbed based on the color and concentration of the solution. So you notice this amount goes in, this much comes out, so the rest is absorbed by this colored solution. More concentrated the solution, the greater the absorbance of light. So the higher the concentration of the solution, the more it's going to absorb, because there's more particles inside that sample that's going to absorb the light and prevent it from going through. So it's going to allow less to get transmitted through. So what Beer-Lambert does, it allows you to do this concept. By using absorbance data, you can figure out the concentration of a solution. And the way you do it is you first would put the sample in by itself. So let's say you're doing Gatorade, for example. You would look at it and you put on a full spectrum and you see what its absorbance is. You see the majority of absorbance is right there, which if you notice data-wise, and this is the information you get from it, the highest peak is 505 nanometers. So 505 nanometers corresponds to what color? So in this situation, it's green. 505 is red, so the color that's going to be best to use to analyze it is green. And the reason for it is that you want to pick a complementary color. So here's what all this means in English. You put your sample in by itself, you get a peak. Whatever the highest peak is, you look at the wavelength, and from there you would figure out what the complementary color is. So 505, for whatever reason, gives you the wavelength of green, so you're here. And then what you do, you pick the complementary color to green, which is red. So that means that when you're putting your spectrophotometer, you would make sure you shine red light through it. And the reason you want to pick red light is because red light can give you the best piece of data, and that's based on wherever this peak is. That's what this allows you to do. All right, so you do this, what's called a dilution. You take that sample, you dilute it to different concentration numbers. So very specific concentration numbers. You know, so you're going from 0 to 0.15. So they're changing by 0.15 each time. The reason you want to do that, you want to make a nice graph out of it, a linear graph to be exact. So you have 4 different dilutions. You make a graph using the data, and these are the absorbance information you get from it. You're also going to do one for your unknown. So I give you an unknown sample, you put it in there, and it gives you 0.39. Remember, these are all the same sample, meaning the same type of chemical for all of them. So these unknowns are just watered down versions of each other. And this is another version of that same color, but you don't know the concentration, you just know the absorbance data. You can kind of tell this is between these two. So you can kind of ballpark it ahead of time and assume your concentration of this unknown is between 1.5 and 3.0. But you want an exact number. You don't want to guess. So how do you do that? You make a graph based on that data. Here's my different points, 1, 2, 3, 4. Best fit line. So even if some of the points, you can see this was a little bit off, we still draw a best fit line through all of them. And what this tells us is basic absorbance basis concentration. The equation for this, because it's a straight line, is y equals 1.64x minus 0.02. Substitute for x and y. So absorbance is going to be your your y-axis is going to be absorbance. Your 1.64x, x represents concentration. I just got that from the graph. So this is the actual formula you're using. This is what it's based on. This is the actual value. The 0.02 is the point intercept, which is right there, y-intercept. So to get the concentration of the unknown, you're going to rearrange this formula right here to solve for that concentration. So concentration, which is this part, is going to equal to, you take 1.64 and divide it out, and you add 0.002. That's what I did here. So this is the actual formula you're going to use to figure out this concentration. When you plugged in your number, so 0.39 was the absorbance. If you notice in the previous slide, this was my absorbance, 0.39. I'm going to plug it into this equation, and I'm going to add 0.002, divide by 1.64, and there's my concentration. So that's how you determine the concentration of an unknown chemical using spectrophotometry, which is basically light shining through a solution. There's your original data point. And that is quantum in a nutshell.